Okay, so this video is concerned with an illustration of modes of stochastic convergence, and I'm going to focus on two modes of stochastic convergence: convergence in probability, denoted by this right arrow P, and convergence almost surely, right arrow AS. You can take a look at these issues, for instance, in Hayashi's book, and he discusses these issues in chapter 2, pages 88 following. But the exposition in Hayashi's book, and also in other econometrics and statistics textbooks, is, I think, a bit dry, and it lacks a bit the intuition behind the concepts, behind these concepts, and I want to supply the intuition in this video. So, stochastic convergence is concerned with the convergence of a random sequence. The random sequence consists of random variables, and we're interested in seeing what happens if the elements of the sequence, which chain together, if the number of elements in the sequence gets large. Can we say something about the random variable at the end of the sequence? And that's what both what every notion of stochastic convergence is all about. Now, convergence probability and almost sure convergence are two notions of stochastic convergence. Hayashi considers the third one, which is convergence in the mean square. We don't do that here. I omit that. You can look it up in Hayashi, and when you have understood what convergence in probability means and convergence almost surely mean, I'm sure you will also you will be able to understand also intuitively what convergence in the mean square is. Later on, we're also going to take a look at convergence and distribution, but not for now. What I'm going to use is, I use the law of large numbers as an illustration for convergence and probability and almost sure convergence. There are laws of large numbers which are called strong. That would be a notion associated with almost sure convergence, and laws of large numbers which are called weak, and these are associated with the notion of convergence in probability. Now, let me first, before we start with that, stress a bit the importance of the concepts convergence in probability and convergence almost surely. One of the uses of these modes of stochastic convergence is assessing the quality of estimators. So if theta hat T denotes an estimator, maybe ML, maybe OLS, based on a sample of size T, one of the requirements that we often have for estimators is that they converge in probability to the true parameter value theta naught. This is a real number if it's one parameter. Theta hat T is a random variable because it depends on the data, and the data are conceived of as realizations of a random process. So that makes the estimators as a function of the data random variables themselves. And now we're interested in what happens if we increase the sample size T and we have this sequence of estimators. What happens with them? If T gets big? Now, if we have a convergence in probability to the true parameter value, we call this weak consistency. And I'm sure that every one of you have heard about the notion, but past experience tells me that students have only a weak intuition about what this term actually means. And I'm trying to provide you with that intuition as we go on. There's also the notion that theta hat, our estimator, may converge in this almost sure sense to the true parameter value. And if we can establish that, we talk about strong consistency. The second area where these notions of almost sure and convergence probability show up is actually associated with the notion of laws of large numbers. Okay. So as an example, suppose that we have a sequence of random variables xn. So we have x1, x2, xn. And suppose this is an IID sequence. So the random variables in the sequence are independent. And moreover, let's assume that the expected value of each of the elements in the sequence is the same because they are identically distributed, and the mean is finite, and we call it a mu. And also suppose that the variance of xi is finite and the same for all, and we denote it by sigma square. Now, what a law of large numbers states is that if you're going to compute sample means using these data, and we denote the sample mean by x over bar n, then what happens with the sample mean, if the sample size grows, we will have a convergence in probability to the expected value of xi, which is mu. Okay, this is called a weak law of large numbers, LLN. As a matter of fact, in this setup, we also have a strong law of large number working for us, where the sample mean also converges in this almost sure sense to the expectation of xi, which is mu, and that would be a strong law of large numbers. Now I'm going to use this as a springboard to illustrate convergence and probability, and almost surely in a graphical with some graphical representations. Okay, that's going to be for later. You may ask, okay, why is it so important that sample means converge to expectation counterparts? Is that something that's really useful for us? Yes, it is. In application of the law of large numbers is, for instance, the assessment whether the OLS estimator is consistent. So the OLS estimator is defined as such. Xi is a vector of explanatory variable, and we have xi prime. We take the sum of these outer products, and we multiply it with this vector xi yi, over which we sum over all observations. So I equal to 1 till n, I equal to 1 till n here. And what we could do with our OLS estimator, we could divide by 1 over n and have 1 over n here. So here's an inverse, so we invert that matrix, which means that the 1 over n comes out of the brackets as n, it cancels out with 1 over n, so I can have the 1 over n's in there or not. But I'd like to have them in to illustrate that the OLS estimator is actually a function of sample means. And what is really important for assessing the quality of your OLS estimation, you want to make sure that this term in brackets has a well-defined probability limit. So if n gets large, we want this term in brackets to converge to its expectation counterpart, to the expectation of xi prime, which is actually a k by k matrix of expected values if you have k explanatory variables in your regression. Similarly, you want this term to converge in probability to the expectation counterpart exi yi, expectation of xi times yi, and this condition actually is important and crucial for the consistency of your OLS estimation. So you want to have a law of large number that works for you using your explanatory variables data and your dependent variable data. Similarly, for maximum likelihood, what you have when you do maximum likelihood, you have a log likelihood function, which is a log of the density of the variable yt evaluated at some parameters theta, and you sum over all observations, and that's your your log likelihood function. And this log likelihood function is to be maximized. So you choose values for theta such that the likelihood function is maximized. We do that in many econometrics classes. But you should notice if you maximize this log likelihood function, you could equivalently say that you maximize the average log likelihood function. Oh, by the way, I just saw that I used a t here, so we're sort of in a time series context. So I have time series observation. So I'm going to sum over all time series observation using a time index. So the sample average would then be 1 over t. Previously I used n for the sample size. Here I use t, big T for a sample size. One would be associated with a cross-sectional problem. The other would be associated with a time series problem. So this is what we maximize for maximum likelihood. And what is important for maximum likelihood theory to claim that our estimates that we get by maximizing the log likelihood function are good estimates, consistent estimates. We want this objective function times 1 over t converge in probability or almost surely to the population counterpart, that it would be the expected value of the log of fyt at theta. I recall that the yt, these are the data are random variables. I plug them in some function. This function happens to be a density function, but in the end of the day, ln of f of yt is a random variable. We sum over big T random variables. The likelihood function itself can be conceived of as a random variable. So we have an average over these likelihood contributions, and this sample average, for the sample average, we want to have an expected, we want to have a law of large number working. So sample means, we want to have the sample mean converge to expectation counterpart. Again, this is very important for ML to deliver consistent estimates. Okay, so we saw that in various aspects of econometrics and statistics, the terms and notions of convergence and probability and convergence almost surely show up. And there are definitions out there in the textbooks of convergence and probability and convergence almost surely, but what is a bit lacking is the idea to illustrate what these notions actually mean. And this is what I'm going to do in the next minutes. So I'm going to provide you with an illustration of the notion of almost sure convergence and convergence and probability, and my illustration is going to use a law of large numbers. Okay. As a matter of fact, almost sure and convergence almost surely and convergence and probability are not only associated with laws of large numbers, but with any stochastic sequence. But I think it's helpful to take a look at the problem of a law of large numbers to see what is actually meant by these concepts. So as above, let us assume that we have a sequence of random variables xn. Okay, and again assume that these are IID data. So it's an IID sequence of random variables. And as above, we have a finite mean, we call it mu, and we have a finite variance, we call it sigma square. Okay, now x1, x2, and so forth itself is a random sequence, but for this random sequence, we can't claim that there's any kind of convergence, or at least not a kind of convergence that we talked about here, almost sure convergence or convergence in probability, not for this sequence, but there is a sequence which I can generate from this xn sequence, for which I actually can investigate these modes of stochastic convergence. And that is a sequence of sample means, x over bar n, which I generate from these IID data. So here is a sequence of sample means, which is indexed by the sample size, so x over bar 1, x over bar 2, x over bar n, right? What do these terms signify? Well, x1 is a sample mean using one observation. That would be just x1, right? X over bar 2 would be the average of the first two observations, and generally x over bar n would be the sample mean over the n observations. That's x over bar n. Yet this is another stochastic sequence, right? xi, x1, x2 are random variables. I use a sample mean where I plug these random variables in, and I generate a new sequence of random variables. Okay. And now here comes an illustration of the law of large numbers, and also an illustration of both almost sure convergence and convergence in probability. Okay. Now let me draw a coordinate system. And in this coordinate system, I'm going to draw realizations of the sequence of sample means. So suppose you draw these IID random variables and compute this sample means. What you'll get is a realization of the sample mean sequence. And I'm going to have a sketch of such a possible realization in this coordinate system. But before I do this, what I'm going to do is I'm going to put on the vertical axis mu, which is the expected value of xi. And around this mu, I'm going to draw an epsilon interval. So this is a line where I add on top of mu some small epsilon, and down here I'm going to subtract this epsilon from mu. Okay. So here would be mu minus epsilon. Now comes my realization of the sequence of sample means. I draw this in red. So I start at n equal to 1, take a draw from the distribution of x, compute a sample mean, which is basically x itself. And then I have the next draw, compute the sample mean of the first and the second, and so forth and so forth. And I'm going to plot the sequence of sample means, and it may look like that. Okay. This is what you would get in the present example if you would draw independent data, random variables x, and average them. This is how a realization of the sequence of sample means would look like. So I indicate this as x over bar n. This is my sequence of sample means, the realization, one possible realization. Now what we do when we talk about possible realizations, we basically indicate this sequence of sample means by an omega. And again, you should recall basics of measure theory, where we have this notion of a sample space and a sigma algebra and a probability measure. Okay, and what this small omega is one possible draw from big omega, one possible realization of the sequence of sample means is associated with this one draw out of big omega. It gives me one possible realization of the xi sequence. It gives me one possible realization of my sequence of sample means. Now the importance that we have here is that this is a sequence of real numbers. So conceptually, once omega is drawn, the random experiment is conducted, and all the realizations of the random variables are there, and we plot them in this way down here. Okay. Now what we see is, if we take draws from the distribution this IID distribution and compute this sequence of sample means. We may start from somewhere with our sample mean, but we're going to go and converge into that epsilon interval around mu. It happens sooner or later, depending on the variance of the axis, but it's going to happen sooner or later. In other words, what we're going to find is we're going to find some cutoff point, and I'd like to call this cutoff point n star, and this cutoff point is a function of the epsilon that I choose, that I draw around mu, and it is well dependent on the realization omega, and it's there where after this when n gets bigger than this n star, you always stay in the bound. Okay. Now I like to index this omega with 1, because this is the first realization that I'm going to take a look at. I'm going to take a look at more realizations later. It's a sequence of real numbers which has, as I draw it here, a kind of an ordinary non-stochastic convergence. After a certain point, we stay in an epsilon bound, and that's it. So it's an illustration of non-stochastic convergence that we see here actually. It's associated with something that is random, right? A realization of a random experiment, which gives us the realization, but the sequence itself is non-random. It's a sequence of real numbers. Okay? And now what we're going to do is, this is just one possible realization of this sequence of sample means. The realization could have looked differently. Maybe like that, right? Maybe I had this blue realization, so maybe I start down here, and then we go into the epsilon bound like that. Okay? It's also possible to have this realization of the xi's, hence this realization of the x over bars. And again, for this sequence of real numbers, the blue sequence of real numbers, well, obviously there seems to be this point here, okay, n star, as a function of the epsilon. For this second realization, denoted omega 2, after which this sequence stays in the epsilon interval. So the blue sequence is x over bar n, and I indicated with omega 2, the second realization. It's yet another sequence of real numbers that behaves in a way such that it converges into that interval. It converges, in other words, to mu. Both the red sequence and the blue sequence converge in an ordinary sense towards mu. Okay, and that's sort of the crucial insight behind almost sure convergence. What happens for these two realizations actually happens for any possible realization, right? Formally, we draw these omegas, small omegas, from the sample space, and omega 2 is one draw from big omega, and there are many more. Maybe I have a third one, omega 3, drawn from big omega, and maybe that third realization looks like that. Okay, coming down here, and relatively early, maybe already here, we go into the band, stay there, and we get very close to mu. Here the cutoff point would be around here. So here's my n star of epsilon for realization omega 3. 3 possible realizations plotted in this graph. There are not only 3, there are infinitely many possible realizations that we have. And the point now is, if we can make sure that this ordinary non-stochastic convergence for this sequence of real numbers happens for every possible realization, that is, every omega out of the big omega, we've established what we call almost sure convergence. Now let me write this down formally. Okay, we are able to, if we're able to establish that for all omegas, small omegas, out of the sample space big omega, there exists an n star which is a function of the epsilon that I choose, and it's dependent on the omega that I've drawn, such that the difference between x over bar n and mu in absolute terms is less than epsilon, any small epsilon that I can think of, for all n which are bigger than this cutoff point n star, then we have shown almost sure convergence. Okay, this is what's required for almost sure convergence. Maybe it's a bit of a misnomer to say, okay, it's almost sure. Essentially, it has to happen for every possible realization, so it's really sure convergence. But we've decided to call it almost sure convergence. Okay, and now you may be also be in a situation to more intuitively understand what Hayashi, for instance, means or implies with the definition of almost sure convergence. I've written it in black here, but what you also sometimes see is the definition looks like that. The limit of the stochastic sequence, here xn, is mu, right? Conceive x over bar n of omega as a sequence of real numbers, and the sequence of real numbers has a well-defined limit. So for n going to infinity, this limit is mu. And the point is, it has to happen for every omega. And we write this by saying, okay, the probability of that event to happen, this probability is 1. Okay, and that's your definition of almost sure convergence. Okay. In shorthand notation, we write in this setup x over bar n converges almost surely to mu. So in a very shorthand notation, this is what we mean, illustrated in that graph. Now let us consider convergence in probability. Now, what I'm going to use to illustrate convergence in probability is precisely the same graph that I've used up there for almost sure convergence. As a matter of fact, I just copied the same graph down here and removed some parts that we don't need here. But it's exactly the same graph, the same 3 realizations that we're going to take a look at. Now, to get the idea behind convergence in probability, what we can take a look at is different n's, different sample sizes, and see how many realizations are actually within the epsilon bound. So for instance, let's take a look at this n down here, small n. Okay. When we take a look at this n, we see that none of the 3 series are actually inside of the epsilon bound, right? So 0 out of 3 are in the epsilon and the epsilon interval around mu. 0 out of 3. Now, if we move a bit further on, increase our sample size. Maybe I'm going to go at this point. Go up. I can say, okay. What I'm going to see is that one of the 3 realizations, the black one actually, is in the epsilon bound. The other 2 are outside. So here I see, okay, 1 out of 3 are in. Maybe I'll go a bit further to this point here. Oops. I have a nice line here. When you go to this point, I'm going to see that, okay, now the black and the blue are in, the red are not yet in, but 2 out of 3 are in the epsilon bound. And at this large n here, say, all 3 are in. 3 out of 3 are in. 0 out of 3 in, 1 of 3 in, 2 of 3 in, 3 of 3 in. And that is a fundamental idea, that reflects a fundamental idea of convergence in probability. Okay. The relative frequencies of series which are in the bounds with a small n is 0. Next, 1 over 3, then 2 over 3, then 100%. Now, if you conceive these relative frequencies as probabilities, which you could if you assume that we do not observe only 3 realizations, but many, infinitely many of them, and we count basically how many of these sequencers would be in the interval, these relative frequencies become probabilities. And what we essentially want to see if we have convergence probability is that in the end, if n is increased, we're getting to the point that the relative frequency, i.e. probability of the sequences in the bounds, converges to 100%. Put differently, the relative frequencies of those sequences outside of the bounds go to 0, probability go to 0 of observing a realization out of the epsilon bound when n gets very, very big. And that's the fundamental notion and the fundamental idea behind convergence in probability. Okay. Now, we can write down the formal definition of convergence in probability, and then hopefully this definition makes more sense to you. So I'm going to take a look at the event that x over bar n deviates from mu in absolute terms more than epsilon. So I'm staying outside of the epsilon bound. And what I'm going to take a look at, I'm going to take a look at the probability of this event when n gets big. Okay, what happens to the sequence of probabilities? So I'm going to take a look at the limit of this sequence of probabilities. And what should happen if I have convergence of probability is that these probabilities go to 0. Okay. And if this is true, then we say, okay, I have a convergence in probability of that stochastic sequence to the limit mu. Okay, x over bar n is a random sequence, mu is non-random. I have this convergence in probability. But what you again could conceive this mode of convergence, which is associated with the random sequence x over bar n. You could also say, okay, what I'm going to take a look at here is a convergence of something that is non-random and a convergence in an ordinary sense. And the sequence of non-random variables that converges in this ordinary sense is actually this sequence of probabilities. And I can denote this with P sub n. It's a sequence of probabilities that, as a matter of fact, converges in a non-stochastic sense. Well, we can illustrate this graphically if we want. So I have an n here, and here I plot pn's. Here is 0. I want to have a 1 here, because, well, the sequence cannot get bigger than 1. So what convergence probability actually means is the sequence of probabilities that I have, and that I compute for an increasing sample size, of the probabilities of staying outside of the epsilon bounds, this sequence goes to 0. So if I draw an epsilon interval in the graph, so 0 plus epsilon, what happens is that if you have convergence probability, you start with a probability that is pretty high of being outside of the bound, but what then happens is that this probability goes down and it goes in the epsilon bound and goes, actually, matter of fact, to 0. I don't have to have a negative epsilon because probabilities are per definition bigger than 0. So this is a non-random sequence of probabilities. And this non-random sequence of probabilities converges in an ordinary sense. So again, I can find such a cutoff point n star, which depends on my epsilon, after which the sequence stays in the bounds. Okay, so after that, the deviation from of epsilon, the deviation of the probability from epsilon is smaller, and it stays smaller. So it's again a non-random convergence that we observe here. It's associated with stochastic convergence, right? It's still x over bar n, it's a stochastic sequence, but we can relate this stochastic convergence to an ordinary non-random convergence, but in this context, it's going to be a sequence of probabilities that we're going to take a look at. Okay? This is one of the useful illustrations of convergence and probability. I find another one pretty useful, so I'm going to present you yet another illustration of convergence and probability, which I hope you find useful. So here's the second illustration of convergence and probability. And again, it's useful to take a look at the graph from above, where I have these three realizations put in. Now imagine you don't have only three realizations, but many, many of them. And you again take a look at these different points here, these four yellow marked points, and you're interested in the distribution of these sample means for a given n. So at this first point here, we see these three sample means plotted. Imagine many more, and imagine drawing a density over these observations. So I'm trying to do that and say, okay, when I want to draw a density over the possible realizations, this density may look something like that, right? It's a really flat density that may look something like that. There's a wide range of possibilities what x over bar can be for this relatively small n. Now, if I move to the right, that is, I consider a larger sample size, and again, I'm going to take a look at the distribution of the sample means across these different realizations. What happens is, in my graph, that the variation of the sample means gets smaller, right? They get more clustered, maybe around mu, and if I draw a density over these larger n, maybe this density will look like that. More peaked, nicer peaked, and maybe something like that. Okay, so at this bigger n, the density gets more peaked, less variation in the sample means is observed, right? And now take a look at this area down here, right, where we see, okay, the three realizations are much closer together. Now imagine many more realizations. They will also be clustered closer together, and if I draw a density over these observations, it gets even more peaked, and maybe the density will look something like that. More peaked around mu still, and maybe something like that. You see how more and more peaked the density gets, the more I increase n. Now at this last point that we considered, right down here, we're going to see that these the three realizations are really close together, really close around mu. And if I draw a density over many realizations of these sample means, this density would get extremely peaked, right? Very almost all probability mass is centered around a very small area around mu. So maybe I can attempt to draw another very peaked density around this point. So I'm start here and I'll go really up, far up, see how very much peaked those, how very peaked this density is, how very dense the x over bar n's of different realizations would be clustered around mu. And I think this is also a nice illustration of convergence and probability, because you can imagine what happens if n gets really, really big, if n approaches to infinity. Then all the probability mass of x over bar n gets allocated around mu. Right? The probability mass collapses to that point. We say the distribution is actually degenerate, it almost has no variance anymore. All the probability mass lies on one point in the limit. And we can try to put this insight in another illustration, where I draw the densities of the x over bar n's at different points n, different sample sizes, and to see how it works. So maybe for a small n, maybe that would be the density of x over bar, say 10. What we get is a very, very flat density, maybe something like that, with a lot of variation of the x over bars, maybe some peak around mu, but there's a lot of probability mass which is away from mu. Now if I would increase n, so fx over bar, say n is equal to 100, what we should observe if you have convergence and probability, then this distribution of x over bar n gets more centered around mu, and maybe we can draw it like that, right? Something like this can happen. Oh, I used a wrong color here, so that would be f x over 100. So you can imagine to look like that. If we increase n even further, so say f of x over bar, say 1000, let me use a different color again, so n gets even bigger, then the density gets more centered around mu, and if I try to paint this, something like that should happen. More and more probability mass gets centered around mu. Maybe it looks something like that. Now the point is, with convergence and probability, if you increase n to the limit, if you let n go to infinity, the probability mass collapses at the point mu. The densities actually degenerate. There's little variation, little variance left over there, and all the probability mass is centered around mu. So let me try to depict this also. So of x over bar for n, say very big, we have this degenerate distribution and the fact that all the probability mass gets centered around mu. So again, I'm trying to illustrate this. There's almost no probability mass, not in the very close proximity of mu. So I'm going to go really, really up and go really steep down here. That's what's going to happen. Okay. What happens is the distribution degenerates. It's not really distribution anymore. All its probability mass is around the point mu. And this is a very, very important, very important insight, which is going to be important when we talk about central limit theorems. What happens if you have what happens to a sample mean if n gets big? What about its distribution? One of the answers that students regularly give is, oh yeah, well that's our central limit theorem working for me, and the distribution of the sample mean is approaching the normal distribution. Well, that is not quite true. When you take a look at this, at the plot that we see here, the distribution of the sample mean in the limit degenerates. Okay, let me put this again. The distribution in words. The distribution of x over bar n degenerates for n going to infinity. There is no distribution left that becomes normal or whatever. This is why the central limit theorem never makes a statement about x over bar n itself, because for a central limit theorem to work, you actually have a law of large number working for you too, right? So x over bar n has a degenerate distribution. If you want to have something that has a non-degenerate distribution, you need to counter the decrease of variation, the centering of the distribution around a fixed point, by blowing up the variance of the random variable. And this actually is achieved by the following operation. So I'm going to take a look at x over bar n. I subtract mu, and as I said, what happens with this random variable x over bar n minus mu is that all of the probability mass of this random variable gets collapsed around 0, right? I subtract mu. So what I do is, or what we do in statistics is, we blow up this random variable, we multiply this random variable which has a degenerate distribution by square root of n, by the square root of the sample size. And this object has a non-degenerate distribution. Or non-degenerate limit distribution. Limit means n goes to infinity. Okay, this is a it's a non-degenerate limit distribution. Let me put that here as well. X over bar n has a degenerate limit distribution. Blowing up the sample mean by square root of n gives you something that has a non-degenerate limit distribution. As a matter of fact, the limit distribution that we have is going to be the normal distribution. X over bar n itself is not converging to a normal distribution, but it converges to a distribution that is degenerate. We need to counter that degeneration by increasing the variance, and the increasing of the variance is done by multiplying the random variable bits with the square root of n. That entails I'm increasing the variance by a rate of n, and that counters the degeneration of the limit distribution. This is something that we have to talk more about when we talk about convergence distribution, indicated by this right arrow D sign. That's something that we're going to discuss a bit later. These issues of degenerate distributions, what do we have to do in order to counter the degeneration of a statistics of interest, is going to be a very important topic when in a time series class, when we talk about dealing with the so-called unit root processes. But these things are for later. Okay, so for the time being, that's it with respect to explanations regarding the two modes of stochastic convergence, almost surely and in probability. And I hope you find these illustrations behind the formulas that you find in the textbooks helpful to understand what's going on. Thank you for watching the video.